here. Today we are going to talk about something called orbital hybridization, or the blending of different orbitals. Remember, when we're talking orbitals, we're talking the S, P, D, and F orbitals that we learned about last year in pre-AP chemistry. And why are we learning about this? Well, previously we learned about the molecular geometry of our molecules, what they look like. And the reason they look like that, or are able to take that shape, is because of what we call orbital hybridization. So today's lecture is going to explain how the molecules actually got the shapes that we talked about the other day. So let's go ahead and get going on this. All right, when we think about hybridization, hybrid is just a blend of two or more things. For example, my wife has a Honda CR-V hybrid. What's hybrid mean? Well, it's a blending of electric and gas motors, and that's all we mean by hybrid. It's just a blending of things. When we talk about it as far as chemistry goes, what we see is that during bonding, when we're making these molecules, these different atomic orbitals we talked about, the sp and df, undergo hybridization. They mix with each other and end up actually forming a new type of orbital, and that's what we're going to talk about today. And so, as I said, if we have more than two atoms that are involved in a molecule, okay, the shapes of the orbitals must match the shape that we predicted. Are they trigonal? Are they tetrahedral? Are they bipyramidal? Okay, and the orbitals sp, d, and f, as they stand straight out, won't give us a shape. So they have to kind of form these brand new orbitals that allow them to do that. Okay, so these sp, d, and f get mixed together. For AP Chem, all we are going to worry about are the S and P hybridization. We're not going to bring in the D's and F, but understand that they will make these hybridization orbitals as well. Okay, and so what we see is that these new hybrid orbitals that form, okay, are going to correspond with these molecular shapes, right? We have tetrahedral, we have a linear-ish, here's a linear. This is kind of a trigonal planar with another trigonal planar, which comes out to be bipyramidal. And that's what we're going to be talking about today. Okay, so orbital hybridization, as I said, is just a mixing of two or more orbits to form a new set of these hybrid orbitals, a new kind of hybrid between the S and P. And what we see, we have to have a mixing of at least two non-equivalent orbitals. The S and P is all we're going to, or the P and D, or the D and F's. We're only going to worry about the S and P's for us. Okay? And what we see is that when we form these orbitals, they have a different shape than the original. Remember, the S one we said was a spear shape. The P was kind of like a dumbbell. When they hybrid, they take on a new shape, and they also take on new energy levels or new energy values. Remember, we said P has more than S and D has more than P as far as energy and so on. Well, what we see is when we form the S and P orbitals, they form an energy level somewhere in the middle of S and P. Okay, so here's our original shapes, but when they blend, they're going to form brand new shapes that we don't observe in here. Okay, so what we say is that these new orbitals that all form the same energy level, what we call degenerate or equal energy level. So that energy level is going to be somewhere between what the P's would have, less than the P's, but more than the S. And you'll see this as we go along. Okay, there are a couple types of hybrids we're going to worry about. Three of them, actually. Okay, and what we see is that the number of these hybrid orbitals that form is equal to the number of pure atomic orbitals in a hybrid. So the number of pure S's plus the number of pure P's is going to be equal to this new formation. Okay, the first type is what we call an sp. And an sp orbital is made up of one S and one P. Okay, they mix together to form this sp orbital. And then we leave two P orbitals that aren't used in this. We actually see them being used in double bonds, which we'll talk about a little bit later. The second type is what we call an sp2. That's one S and two P orbitals to mix to form three sp2. And then this leaves an extra P orbital out there. And then finally, the third type is what we call an sp3, one S and three P orbitals mixed to form four sp3 orbitals. And the process of figuring out which type of orbital form is really easy, and we'll get into that in just a minute or two. Okay, and as I said, there are additional types of these orbitals, the D and S, but for AP Chem, we do not need to worry about those. But understand, Maybe sometime in your chemistry career you'll hear about them as well. So let's look at the sp orbital. As we said, these sp hybrid orbitals are formed by the hybridization of one s and two p's. And so what we see is if we have two s here, we actually are going to end up filling one of these p orbitals with 1a electrons, and they form this hybridization here, this sp orbital. Okay, 1s, 1p gives us two sp orbitals. Okay, the angle between these is 180 degrees. So I need to memorize this, not exactly, but if you think of a linear molecule, right, it's 180 degrees between them, and this is why, because they have an sp orbital. So here we go. Here's a good example of a linear. Here's our 180 degrees. Here's our S. Here's our P. When they put together, they form something that looks like this, which is our sp orbital. Okay, our next type is an sp2. Remember, an sp2 is one s orbital and two p orbitals. So we have, here's our two s's, our p's, and we're going to form 1, 2, 3 sp orbitals. sp2 orbitals, excuse me. The angle with these is about 120 degrees, kind of like a trigonal planar. Okay, so here's our s, here's our two p's, and when they form, we get something that looks like this. There's our trigonal planar right there, the 120 degrees between them. And then finally, the last type is an sp3, and that's made up of 1s and 3p orbitals. Okay, we get an angle about 109.5 between those. We got two s's, two p's, and they come together to form this sp3. Notice here we have one leftover. Okay, so we'll have one leftover orbital there. That'll come important later. And here's our s, and here's our how they end up forming that tetrahedral shape there, that 3D looking pyramidal shape. Okay, so here's just a picture showing our three, the SP, SP2, and SP3, kind of how they come together and how they form, just a little reference for you. Okay, so now the important part as far as AP goes is how do we determine what hybridization is really easy? And it goes back to basically what we are doing with Vesper. We got to look at what's around the atom that we're into. We look at what we call regions of high electron density. So what we talked about are domains or our steric numbers. Okay, and remember, these electron densities can either be a bond between two atoms or they can be lone pairs. So we're going to have our Lewis structure drawn out to be able to do these. And these electron densities, they're all equal. Okay, it doesn't matter if we have a single bond, a double bond, triple bond, or just a lone pair. They are all equal to 1 when we're counting up for this hybridization. Okay, so if there are 4 regions around the atom that we're interested in, we're going to have an sp3. Here's 3 plus 1 gives us 4. Okay, if we have 3 regions around it, we're going to have an sp2. Think about 2 plus 1 gives us 3 regions. And then finally, if we have 2 regions, it's going to be an S and P. So it's really easy to tell. Just figure out how many domains are around your atom that you're interested in, and then put that into here. Here's 4, here's 3, there's 2. And that's about as complicated as it gets for us in determining this. So let's look at a couple examples here. Let's look at our first one, methane. Around our central atom of carbon, we have 1, 2, 3, 4 domains. How do we get that? Well, 1s, S is always 1, and 3p. So this is an sp3. Water, on the other hand, let's look at this. We have 1 lone pair, 2 lone pairs, then we have 2 bonds. So 3, 4. So once again, it's just like methane there, we have an sp3. Finally, if we look at this last one, if we look at it from the perspective of this carbon here, carbon has 1 domain and 2 domains. How do we get that? Well, that's an sp. Pretty simple there, I think. Okay, let me have you try this one on your own. Go ahead and pause in just a second and look at it from the perspective of the highlighted atom here. So go ahead and pause and come back. All right, beryllium. We have 1, 2, so we're going to have an sp there. Boron, 1, 2, 3, so 1s. We got 2 more, so sp2. And then nitrogen here, we have 1, 2, 3 bonds plus 1 lone pair, that's 4. So it's going to be sp3 for a total of 4. Pretty simple to figure this out once you have the Lewis diagram. But you got to be confident drawing your Lewis diagram to be able to do this correctly. All right, let's kind of talk about different types of covalent bonds here. We talked about covalent bonds previously. We talked about single bonds, double bonds, triple bonds. Well, let's talk about more specifically what's going on in each of those types of bonds. There are two types we're going to talk about today, a sigma bond and a pi bond. There's our little symbol for sigma, keep that in mind. Sigma bonds, it's a covalent bond that forms by the overlapping of orbitals along what we call the end-to-end axis. So if we look at here, here's hydrogen chloride. This is the axis we're talking. We're overlapping here. Here is chlorine gas, the diatomic molecule, overlapping here. And what we see that sigma bonds are formed by a single bond. Okay, we say that this bond is formed around the line of electron density, where it's most dense, is concentrated symmetrically along the line connecting the two atoms, this internucleus axis that we talked about. So sigma bonds are always what's formed when we have just a single bond. Okay, and once again, they're made from these overlapping, so it's a hybridized orbital as well. Our second type of bond is a pi bond. Here's that inner axis. So what we can see is that it's actually above and below that. Okay, so it's a little bit different location. The pi bond uses symbol pi, of course. It's a covalent bond that's formed by the parallel or side-by-side overlap of these two p orbitals. So here's our orbitals here. There's our overlap. Okay. Remember we talked about earlier what we had when we formed our hybridization. We had leftover p orbitals that weren't part of it. Well, this is where those p orbitals are coming in. They're overlapping here, and that's what we mean by leftover p orbitals. Okay. And as we said, this pi bond is going to exist above and below this interstellar axis. Okay. And so sigma bonds would be here. Pi bonds are up top there. Here we go. Here's a picture. Here's our sigma bond. Okay, along the axis, and our pi bonds are forming above and below. Okay, pi bonds come in when we have double and triple bonds. Sigma bonds then are only with single bonds. Okay, because the fact that the pi bonds are above and below that interstellar or internuclear axis there, they're weaker than sigma bonds. Okay, because the overlap is less effective than the end-to-end overlap. It's not as strong, so pi bonds are weaker. And as I said earlier, all sigma bonds are considered to be single bonds are considered to be sigma bonds. Double bonds and triple bonds are where the pi comes in. So a double bond is going to have one single bond or sigma bond along that axis, and then it's going to have one pi bond up top. A triple bond then has one sigma bond and two pi bonds on it. So pretty easy that way. Okay, so here we go. Here's our sigma bond here. Okay, this would be a sigma bond there as well. And then here's our pi bond is up. It's a triple bond, so one bond there. And then here's one pi, there's our other pi bond. So this bond right here is made up of one sigma and two pi bonds. Okay, so let's do a couple practice on this. Excuse me. Question says, how many sigma and pi bonds are there in acetic acid or vinegar? So first thing we have to be able to do is to draw the Lewis structure for that. And I'll give you this one because it's a little more complicated. Okay, the question is, now, how many sigma bonds? So first thing we have to do is identify all our sigma bonds. Okay, so right here are all the obvious ones, right? So we got 1, 2, 3, 4, 5, 6 there. But remember, we also have this bond here. So there are 6 single bonds, but in this double bond, then we have one sigma bond. So that's going to add, gives a total of 7 sigma bonds. And then there's also a pi bond there. So we have one pi bond in there. And that's how you count these up. And they'll often ask you a question like this on the AP exam. Let's try one more together. How many sigma pi bonds are in ethane? If we look at ethane, we got 2 carbons and hydrogen. The carbons are going to be connected together, and the hydrogens are going to come off the carbons. It looks something like this. All right, so let's start by counting our single bonds. We have one here. We have another one here, and then we got a triple bond. Remember, triple bond is always one sigma bond. Okay, so we have 3 sigma bonds, and now we have 2 more bonds, and both those bonds are going to be pi bonds. So we have 2 pi bonds, so 3 sigmas and then 2 pi bonds in this. All right, let me have you try this one on your own. Okay, ethylene, draw the structure for it, very similar to what we just did. Okay, what type of hybridization do the carbon atoms show? And then finally, how many sigma and pi bonds are in this? So go ahead and pause this. Come back when you're ready. All right, hopefully you paused and didn't cheat. I know some of you cheating out there. Stop now and do it on your own. All right, so here's our Lewis structure. Okay, we got to remember FN, the last one we had a triple bond here. Here we only have a double bond. So what type of hybridization did carbon does? Well, let's look at this carbon. It's got 1, 2, 3 domains. That's how we get 3. We got 1 s, and we got p's. How many do we need? 2. So we got sp2 orbitals, and we're going to have 3 of those hybrid sp orbitals. Now, how many sigma and pi bonds under it? Let's do singles first. We have 1, 2, 3, 4, and then remember one's here. It's 5 sigma, and then we're going to have 1 pi bond in there as well. So hopefully this wasn't too hard for you. Going back to that, so just a little on that. Okay, try this on your own with CO2. Give me the Lewis diagram for it. Tell me the molecular geometry shape. What shape is it? What hybridization exists? And then finally, how many sigma and pi bonds? So go ahead and pause it and come back and when you're ready. Right? So go ahead and pause. All right. Here we go. So let's see what we got here. The Lewis diagram, CO2. Okay, we got straight molecular geometry. Well, we got straight there, so that's going to be a linear, right? 180 degrees. Hybridization. Carbon has 1, 2 domains. So how do we get 2? 1s and 1p, so it's sp. Number of sigma bonds. Well, let's see. We have 1 bond here and 1 bond here, so that's 2 sigmas. And then we also have double bonds, so it's 2 pi bonds as well. Okay, and so you can see in these diagrams here, we're looking at the carbon and the oxygen. The colored ones, the yellow here, or the green here, those are your hybridization. And then here's our leftover. This is where our pi bonds are forming on these leftover pi's, so what we're talking about. And this is kind of what we end up seeing. Here's our 1 sigma bond, here's another, here's our pi bonds, here's our pi. All right, guys, so we talked about a lot today. We talked about what is hybridization. It's the orbitals that form from a combining of the s and p in our cases in order to allow us to get these molecular shapes. We talked about how to figure out the hybridization by counting the number of domains around it, whether that's a lone pair or bonds, and then putting that into our SPs, right? And then from there we talked about the types of bonds that actually exist within the covalent, the sigma and the pi bonds. Remember, all single bonds are sigma bonds. And then if we have a double bond, we have 1 sigma and 1 pi. A triple bond, we have 1 sigma and 2 pi bonds in there. All right, guys, if you have any questions, please let me know. Otherwise, I will talk to you soon. Take care.